Hello?
Hi there.
Hello? Can you hear me? I get no feedback, so I don't know what's going on.
Hi, Evan. We're here. We can hear you fine. Can you hear
Okay.
us?
Yep, I can hear you. Okay, I'll go ahead and start.
Great.
Yep, I can hear you. Okay,
All
I'll
right.
go ahead and start.
Thank you.
Okay, I'll just have to assume that you can see that. If you can't, please pop open the sound and let me know. This is a little weird. It's like I'm talking to myself because I have no feedback, no audio, no video from you guys, so we'll give this a go and see what happens. Okay, my name's Evan Phoenix. I work for Splice now. At the time I wrote Puma. I worked for Engineered, so I worked at a number of different places. I worked for Living Social for a while. So I'm just going to be talking sort of about Puma, why I wrote it, what it does, how it compares to other web servers, and then at the end we'll hopefully be able to do some questions, and maybe I can show you some various other things. I guess you were playing with Puma during the last talk, so maybe I can clear something up there. Anyway, let's go on. So, why write Puma? Well, at the time, and this would have been 2011, 2000, yeah, maybe 2010. Unicorn was really the state of the art, and for many people, it continues to be. But it's a process-only model, and it was really built to work around. It was built to be the fastest web server for MRI C Ruby as possible. And so it was really tuned for that specific workload. Everything, all the performance implications of that it was tuned for. And I was at the time building Rubinius 2.0, which has no global interpreter lock, has truly parallel threads, the same as JRuby does. And so I really wanted a web server that would be able to utilize those threads well, and because that would really show off Rubinius. That was the plan. That was the big push, was Rubinius 2.0 is coming out. We need something that people can use to run their web apps on Rubinius 2.0 and really get a lot of benefits. So as I started on that, I decided that what I would do is I would build on Mongrel. That's where I would start. Mongrel, if you're new to Ruby, was a web server created by Zed Shah back in 2007, 2008 maybe, that had really great bones. By that I mean it had a really good parser. It already used threads. It was very close to what I wanted, and really what I saw Puma as sort of a modern Mongrel. It was sort of taking Mongrel and bringing it forward to where the state of Ruby web apps was. A big part of that was obviously Rack. Mongrel was written pre-Rack, so it didn't handle Rack apps at all. It was actually it had its own system for how to hook into it and all of its routing and all that kind of stuff. So a lot of code got deleted out of Mongrel, and that kind of became Puma. And so it was really building on the shoulders of Mongrel. And a big part of it was adding thread pooling. So Mongrel used threads, but it was really written, Mongrel was written mostly for Ruby 1.8, or entirely for Ruby 1.8. And so it would spin up a thread every single time a request came in. Now, in Ruby 1.8, that was actually not that big a deal because the threads were green threads. They were actually fairly cheap to create. In Ruby 1.9 and Ruby 2.0, and as well Rubinius and JRuby, you don't really want to spin up a new thread every single time a request comes in. That actually that creates tons of problems. So I added thread pooling with the sort of seeing them as the threads aren't free. You can't just spin them up and immediately have something there. They take up memory, they take up resources just to create and all that kind of stuff. So I added a thread pool in to actually manage them, and that thread pool gives you a lot of. You can tune that thread pool, and it will give you a lot of sort of interesting semantics about what kind of performance you get and all kinds of various things. So we kind of get to Puma 1.0. Like I said, mostly built for Rubinius. It was a pretty small core. But I had built it to work on all Ruby implementations, and that's still true today. It works on Rubinius, JRuby, MRI. That would be Ruby 1.8 all the way up to Ruby 2.1.2, as well as sort of the other sort of smaller implementations. It works on maglev. There's actually a version of it that I know that some people use on maglev, which is a sort of small talkish implementation. So it wasn't, so 1.0 was actually pretty small. It was really just sort of the retrofit on top of Mongrel. So a quick little deviation before we get to Ruby 2.0 or Puma 2.0. So I kind of alluded to it earlier about sort of how the threading works when I was talking about Rubinius 2.0. Specifically about the global interpreter lock, and actually, technically that's what Python calls it, and myself has been calling it in Ruby as well. They actually call it the GVL, which is for global VM lock, I think, inside in MRI if you're looking in the code. But basically, what it does is it prevents threads from being truly parallel. So, like a good example is. If you've got two threads rendering templates, they'll have to wait on each other. They'll actually have to, if you're doing something that's very CPU bound, they'll have to kind of run in lockstep. One will run for a little while, and then it'll give up control, and the other one will run for a little while, and it'll give up control. So you have concurrency, but you don't really have parallelism. And we can get into that discussion at the end here if you want me to get into that a little bit more about what the difference is there. So, but the important part is actually that whenever you go out to do I/O, such as talking to a database, the system releases the GIL while that thread is waiting on I/O, and so other threads can run. And so the realization there is that because most web apps are calling out to databases and doing all kinds of stuff like that, a lot of times they're just blocked. They're really just waiting on getting something back. It's only sort of a fraction of the time that they're actually doing stuff that is sort of CPU bound, that you want to be running stuff at the exact same time. And so you kind of exploit that and use threads and see that for a huge amount of web apps that exist today, threads are a viable concurrency mechanism. Now they're not good for everything. If you have let's say that you want to build the best Fibonacci web app ever, and so people can submit a number and it will compute Fibonacci of that number, then it will give their result back. Obviously, that's a purely CPU-bound activity, and even though your web app may get a lot of venture capital money because it's so amazing, it's not going to run parallel on MRI. You're going to basically, your throughput is going to be limited basically to one thread. So if you got 10, if one request was taking 10 milliseconds and you're doing 10 parallel requests, you reasonably would see many requests take 100 milliseconds because they would basically be waiting on all other 9 threads before they got around to actually computing their Fibonacci number. So the GIL exists, but we don't have to worry about it as much as some people say. It certainly is a limiting factor in MRI, but it's not something that it's something that you can still work around. So as Puma 1.0 was done, and I was thinking about this and where Puma would go from there, I opted to basically add a whole new model in Puma 2.0, which is a hybrid model. And that's because, like I said, if your Fibonacci web app really needs to scale, threads are not going to do it. You're not going to be able to do it with just threads. So 2.0 added a hybrid thread process model, and at that point, Puma was a fairly viable production web server for any Ruby. You could run Puma in effectively the exact same configuration that you run Unicorn now. So basically, you could run it with a thread pool of 0, or a thread pool of 1 rather, and with a number of process workers, and that would work exactly like Unicorn. And actually, we can get into that a little bit too, about what the what the migration from Unicorn to Puma looks like. I'll make a note to talk about that at the end. So okay, so as sort of Puma 2.0 was being done and people were starting to see Puma and ask, could I/should I use this for my particular thing? One of the big questions, especially running on top of Rubinius or JRuby, was, is Rails ready for this? And even though Rails, since I found this out just recently at another talk that I was giving, since Rails, literally the very first commit of Rails has allowed for concurrency, and so there's been that flag that you could toggle on and off. They finally flipped it on by default, I believe, in 4.0. It wasn't totally concurrency ready. So in other words, they knew that they wanted to be able to run it concurrent, and they were working actively to fix any bugs that they had that were concurrency related. But until you actually start to run it actually concurrent, you don't really see the bugs. That's just concurrency bugs are the hardest bugs to find anyway. So people started to try to run their Rails apps on top, apps on top of Puma, and slowly over time we work through the bugs. There's some good bugs. I can furnish some interesting pull request discussions that have gone on for multiple years, where it's like, I don't know how this bug happens, and this one particular one that I ended up fixing in Rails was, something very sticky, something very weird. There's a great example of a concurrency bug in Ruby. So as Rails concurrency got better, it's only getting better over time. People look more to running using Puma because they know that their apps obviously will run fine. Certainly, if you use something like, even if you write like a raw rack app or something like that, you can be concurrent initially. And actually, we had some people who wrote raw rack apps to do something very highly concurrent, say a chat server or something like that. And in the beginning, when Rails wasn't ready. So yeah. So the question that I get most often related to Puma is, how does it compare to Unicorn? And I've got a nice little graph on Puma.io, which I did not include in here, which basically shows that the memory footprint of using Puma versus Unicorn with the same number of concurrent slots, if you will, is night and day. I mean, if you use Unicorn, even with something like the patches that allow it to use copy on write, use MRI to use copy on write and stuff like that, it still is hugely different. It's like 7 to 10 times memory reduction in using Puma. Now those initial tests were done on Rubinius, so obviously the throughput would be fine there, but that wouldn't be true on MRI, and that's fine. Obviously, that's not a totally fair comparison, because on MRI they wouldn't have that full throughput because of the process versus thread model. And so as you look at the hybrid of it, you can easily. So I have one particular company that I know is using Puma, and as we are working through the initial. I helped them through their first usage of it. What I actually recommended they do, and I've got this on the README, or there's a deployment document inside the Puma repo that goes over this, is what people do is they start off basically with a thread pool of 2, and half as many workers. So even if you get a memory reduction of half, which is huge, if you've got, I see lots of installations with like 16 unicorn workers. So if it goes from 16 down to 8, and you're really only using a thread pool of 2, you're very it's not likely you run into concurrency problems. Actually, things for the most part run fine, but you still get a 50% reduction in memory usage. So that can be huge for a lot of people. Okay, so let's see if I've got a couple more slides here. So the features, like I said, hybrid process thread model that allows you a lot of flexibility about how to spin up, how to scale out your app, both sort of horizontally as well as vertically. I like to think of vertically as threads and horizontally as processes. It's got zero downtime deploy, just like Unicorn. It's got 2 actual mechanisms for that. One is sort of the stop and rerun. That's a very simple one where basically it gracefully allows all of the requests to finish. It starts up a new version of itself, and then it transfers control over to the new version. So it's you don't lose any requests, but you sort of get this sort of time spike in the middle while all of them are finishing and while some of them are backing up. And so that's not acceptable for some people. So I added a phased restart, which we can get into more at the end if we want to get into that. That is in the cluster mode. That basically allows the new code to spin up one process worker at a time, and then as one starts, the next one goes. So that way you get a very even, a very controlled restart. One of the other features I consider of Puma is it's a very small core. The code is written in a very easy to read, easy to understand way, and so it's easy to find bugs. It's easy to add features, and I personally consider that a feature because it allows Puma to be agile. So I kind of talked about this earlier. I have a number of companies that are using it in production that have told me about it. I'm sure that number is, hopefully that number is not representative. By that I mean that it's most likely, as with all of these things, that you hear about 5 people using it and it's really 20 or something like that. So, but I get very good feedback from some of those people, and they've been very successful with it. And I'm always looking for input from those users on ways of making Puma better. I actively add features based on what the users request. If they need a particular feature, I recently added, because of going back and forth with a user about improved ways of interacting with Bundler as the actual code restarts. That's a big problem that people have. So some of that was added directly into Puma to improve it, to make it better. That's all the slides that I prepared. I thought we might go over some questions and talk about things. So thanks so much.
So can you hear us?
I can. Can you see me? I can. Can you see me?
Yes, we can.
Yes, ma'am. Yes, ma'am. Oh.
Go ahead. Somebody want to ask a question?
It's still light there.
So
it's still light there.
Yes, it is. So I have a question. I was looking at the source for the project, and I noticed that among other things, there's an HTTP parser in the source itself, which is kind of interesting in the sense that traditionally a lot of that logic is in a higher layer in rack or somewhere else. Would there be a model where one could actually avoid using the rack and still use Puma at this point?
Well, I mean, let's see. I mean, you have to. I mean, rack is HTTP based, so fundamentally it has to be using HTTP in some way, and so it's not. You can't. I mean, the way that it's interfaced is through HTTP directly. So I mean, there's an experimental mode inside Puma that I added for someone that actually lets it use just for raw TCP apps. If you want to just have something that's just raw TCP, but I'm not sure what you mean by without the HTTP part.
just simply meant, was there, so I'm curious how using Puma might change the way that we're thinking about our stack as far as the app is concerned. And I mean, there's a lot of people who are frustrated with Rack and would wish that it would be rewritten or changed in some significant way. And I guess my question was whether there was any possibility of working with Puma without Rack in between.
Okay. I'm gonna. Oh, there you go. Okay, you muted yourself. Perfect. Okay, so I think that's a very good question. So Aaron Patterson and a number of the other guys who work on Rack, and I've talked about this over the years, basically. Right now, Puma is totally Rack. It totally expects Rack. So it's written in a fairly pragmatic way in that it doesn't have a whole bunch of pluggable infrastructure in between the actual parsing and the dispatching to the actual app itself, and the reason is that for performance. It doesn't. It was only meant to do Rack initially, and so it's much easier to have it be specific to Rack inside that middle part. That being said, I actually have said to the other Rack guys that I actively would love if Puma was the initial test bed for a sort of a new version of Rack or a new version of ways of dispatching. Web, the application or the request, that kind of thing. So it's fairly, it's not in there, but that kind of code would be not too difficult to add.
Is it okay if I ask another question?
Sure.
Okay, great. So there was just a presentation by our friend Christian here, and he did a Hello World app in Elixir using framework, and a Hello World app with a rackup with a proc, and showed that the Elixir app was running, what was it, 23,000 requests per second, and the Ruby app was running on Puma, what was it, 2,000 or 3,000 requests per second. Would you be willing to show us any ideas about how we could think about how we could improve that story for our projects?
Sure. I think that that's a good. I suspect this. I didn't see it, but I suspect that what you're seeing there is a lot of Erlang hitting and using multiple threads and running a lot of things in parallel. And so really that's where you kind of want to get into if you're on MRI, is getting into using the actual worker model. So we could do that little exercise and kind of see what it looks like. Let me do a little screen share here, and we can. Is that all right? Is that big enough? Everybody give me a thumbs up if that's big enough. Okay. All right, so let's do. All right, so let's just write the hello world. Actually, I will cheat. So I suspect this is almost identical to the one that was used before. So let's see, what version of Puma do I have installed right now? Okay, that's fine. So so if we run this, let's do it like this. So by default, we see that it's using 16 threads, minimum 0. So basically, what the minimums, the thread pool is configured with minimums and maximums. So what this actually does is it says that if there isn't requests coming in for a certain amount of time, it will start to spin down threads inside the thread pool. And the idea there being that you kind of allow the thread pool is allowed to kind of balloon up and then kind of shrink down based on whatever constraints you give it. So in this particular case, it will shrink down to 0 threads and it will balloon up to 16. In production, a lot of people actually do the same number there. So they'll say like min 8, max 8. And so that will basically allow the thread pool to, it'll stay the same size all the time. So there's no spinning up of threads. They spin up all at the beginning and then that's it. So we're not using any actual other processes here. We're just using the one process, and you can here just the single process. So what? Just so that we're sort of doing apples to apples, what HTTP tool was used to check the request per second?
It was the WRK tool.
Should I go download that? Where is that? Should I go download that? Where is that?
You can brew WRK. Yeah.
Just because otherwise we're going to do a lot of like. Just because otherwise we're going to do a lot of same as this tool. Oh, that's not the same as this tool. So this will take but a moment. So let's see. I made a couple. Sure. Yeah. So I talked about this earlier. The migration from Puma to Unicorn. Never mind. All right, we're good. All right. So let's see. I've never used this tool before. So what option should I give it here?
You could give it -T 10. I was using 10 threads, and then a concurrency factor -C 400, and that was it. And then the URL.
Okay. So it's running on 92.92. So one thing that you saw was I popped in right at the end there. Okay, is there no output, or is it? Oh, it's right there. Let's see. Yeah, so this was request per second was about 5,000. Obviously, we're on different machines, so that's going to be part of the discrepancy there. One thing that is fairly common. Let's see if I go and I do. And I tell it not to log by default. So that bumped it up significantly. That's double. The hello world is so small that a huge world is literally writing the output of the message about. So that's important in this particular case because the workload is so small that the actual log output is as much work as the actual serving of that request. So that's important to note. That's important to note just in general. If you've got some tiny little endpoint that needs to go super fast, you actually want to try and see if you can turn logging off on it, if at all possible, because it will make a huge difference. Obviously, if you've got some kind of request that, if you've got a normal web app, the work of just dispatching to the right controller is going to be more work than actual outputting. So it's not, again, that's not totally apples to oranges there, but that's something to keep in mind. So let's go ahead and we'll get this back and we'll kill it. And now what we can do is we can use the worker. So -W automatically tells it to go into worker mode. So now what we can do is we can just say, okay, I want to go ahead and just use 2 workers. And so now what we see is it booted up with process workers. It let us phase restarts only available in worker mode. And then it booted up 2 individual processes. So now if we go see, we see that there's actually three processes. There's the first one that launches is always just the controller. It doesn't actually serve any requests. It's literally just there to manage the cluster itself, to make sure that things are working the way they should. So now let's go ahead and test that. So now we're doing well. So now we've bumped it up. So we were at 4,000. We got rid of the logging. We went to 8,000, and now we're getting up to 14,000. So we're actually doing pretty well on just adding one additional worker inside there. One additional worker process. So one thing that is I have to open up my process monitor now, because as we start to do this more, we're going to be using the cores on this machine to serve the requests, as well as using the exact same cores to serve the responses. So we're going to start to bottleneck inside there. So let's go ahead and let's just throw caution to the wind, and let's do like 10. So again, we see that they. And let me, hold on, you can't see this, but I'm opening up my, I'm opening up the CPU usage monitor for every single core on this machine so that I can see if they're all pegged or not. They were all pegged. And we got, what, 18,000, something like there. So in this particular case, what has happened here is we started to run into a couple of things. The worker model is not within Erlang. It's always going to be faster than the process worker model. And the reason is just that the process worker model has to do with the fact that the OS is involved in doing a lot of blocking I/O calls in order to actually get the requests. And they actually, there's a phenomenon within operating systems where in this particular case, what you actually get is each of these worker processes are listening on the accept port. They're listening to get, this is the normal Unix mechanism for having multiple processors and handling one server. That actually has there's a problem with that called the thundering herd problem, where what actually happens is they all wake up and only one of them actually gets the new socket, and then they all go back to sleep, and then the next one comes in, they all wake up, and that actually uses a lot of resources. Scanning through, waking them all up, only one of them getting it, all of the rest of them going back to sleep. So you get significant concurrency issues as you kind of get up to the top. Whereas I know that Erlang does not have that problem, because it's going to be all inside one process. It's going to be all using threads to do this. You're going to get one actual I/O thread actually doing the accept, and then it's going to be handing it off to Erlang processes. So that's going to be more efficient than we're ever going to be able to get with processes here. So that's going to be a big reason that I could tune the crap out of this all day and probably never get to 26,000 or whatever it was. That's just because the limitations I'm working with inside Ruby don't allow me to actually get that high. If I were to go and if I were to switch to Rubinius, and I could probably play with it for a little while, and we might get close. But within MRI, it's probably not going to be feasible. One thing that's a little something to notice here that's should kind of stand out is just making sure that we check the standard deviation here. So we have a pretty high standard deviation on these requests, right? A 2-second standard deviation off of an average of 2 seconds is pretty high. And so if it's being reported the way I think it is, and given the fact that the max is 6.8 seconds, it probably is. And the reason there is, again, just that we're doing 400 concurrent connections. So we're going to be blocked. We're only able to service, so again, the math here is we've got 10 workers, and each of those individual workers has in itself a maximum of 16. So we've got 160 possible concurrent slots, if you will, that can be filled. But if this thing is saying do 400 at a time, is that 400 total requests, or is that? Let's see. Connections to keep open. So I assume that is 400 concurrent requests.
Yeah, exactly. That's
okay. So we've only got 160.
So we've only got 160.
So we've got 400 potential requests to do at a time. So you're going to see a fairly high standard deviation because you're going to get a lot of requests that just sit there and waiting for a slot to open up. Obviously, if we tune these, any number of things can happen. So, but the important part here is that adding using the worker mode allows you to scale out amongst your, basically the way to think about it is, and this is what I tell people, is you want to have your workers equivalent or maybe 20% more than the number of cores you have in that machine, if that machine is just doing, serving Ruby at that point. So if you've got an 8-core machine, you probably want to do 10 workers. If you've got a 4-core machine, you probably want to do 5 or 6 or something like that. And the reason being that those processes are basically going to scale. You want them to scale for the operating system as close to as possible within a single core, because that will actually help the operating system be able to manage that sort of process bound to that core as well as possible. And so then once you've got that, you've worked out that, like I said, I've got 4 cores here. If I did 5, that would probably be more economical for my machine. If I do 10, so if I, like I said, I had there 10, what you actually get is within the operating system, you get a lot of thrashing. You get a lot of context switch thrashing between the actual processes, because you've got 10 things that are trying to all run as hot as possible, but you've only got, the operating system only has 4 physical slots to put them in. So you want to try and scale it as close to that as you can, because the operating system will work less and you'll actually get more output. We can just see what happens when I do that. So yeah. Oh, so and then the threads are sort of scaling within that process. Right. So again, we see that we didn't get significantly more. We got 17,000 with 4, with only 4 workers, and we had 10 workers. We got 18,000 workers. So we're actually fast on context switching within the number of cores that we can pass.
Is
yes.
there a way you can tie the Puma processes to individual cores in the CPU, like on Nginx or something?
No, but that would be cool.
Yeah. Okay. And just might add, of course, it is comparing apples and oranges, since the Erlang process model is completely different from what we got here. Here you're scrolling with threads inside the operating system and processes in the operating system. Erlang processes are much more light to start. You can spawn it off way faster than the operating system. So yeah, it is apples and oranges.
Yeah, but I think that what knowledge there are. How can you tune this? How can you tune it based off just what mechanisms we have?
That's awesome.
What does this story look like on Rubinius or JRuby? One of the things I ran into when I was trying to use Puma was I was using SQL for my database library, and I couldn't for the life of me figure out what I was supposed to do as far as disconnecting from my thread connections to from my thread pool, and how to think about threading. I just didn't understand how the different layers interacted with each other.
Yeah, so that's tough. So the big thing is that inside there's actually a middleware that manages, a rack middleware that actually manages the database connections that will actually return them back in. And so that's actually a really good model. I suggest that if you're using SQL or some other database, that you actually use something very similar. You just use a rack middleware that will return that thread's connection back into the pool. And I haven't used SQL enough to know exactly what that looks like. That doesn't really matter whether or not you're on JRuby or Rubinius or MRI, whatever. That's effectively the same. It looks the same. From a concurrency perspective, if I was on Rubinius or JRuby, I wouldn't even bother to do workers for this hello world. I wouldn't. If I did 4 workers versus no workers, with it almost wouldn't matter. I would see probably the same performance. I might see better performance with actually no workers even. And if we want, we can do that. I don't want to keep you guys too late. But yeah, it would look about the same, mostly because within Rubinius and JRuby, they're going to be run fully concurrent. So those threads are going to be, if my CPU meter is going to show that one process, that one JRuby or Rubinius process is using basically 400%. I have 4 cores in this machine, so it would be using 400% of the CPU. It would just be maxing it out because there's no GIL. Those threads are able to run fully, sort of unleashed, if you will.
So sidetracking a little bit, how production ready is Rubinius?
I think it's quite production ready. I mean, I think it's quite production ready. I mean, I get people telling me that they're using it in production. I've had some people using it in production for years now. I haven't talked to him about this, so I won't mention him by name in case he cares. But I've got a friend that's using it at a fairly large company to handle a large amount of traffic, and he's actually very good about. He lets me know, oh, everything's running fine. You know, we're running a huge. We had a huge spike today, and everything kept up fine. So I'm getting good results, good data from people running in production. That everything is actually working quite well. So.
Come on, guys.
How many threads would you recommend running per worker?
It depends on your app. I think that the default of 0.16 is a really good place to start. And then I think that the best thing to do is to actually do some experimentation for your app. Make it bigger, make it smaller. Largely, you're talking about the max. The min isn't going to matter too much because you want to know how much concurrency you can get through it. If you're on MRI, then the number of threads is going to sort of dictate how many requests you want that process to be waiting for I/O with, because you're never going to run them in parallel, right? With JRuby or Rubinius, the number of threads is effectively the same as the number of cores. And so it's it's the number of cores times the number of concurrent requests that you want. So in other words, if you've got, like I said, we did 4 workers with 16. If that's where you want, if you want to have, 50. I know that math doesn't work out, but let's say you want to allow this particular one to have 50 concurrent requests. You set the thread pool at 50. So it's easier calculation on MRI or on JRuby and Rubinius and MRI, but it's something that it's difficult to know. There's no universal number. Like I said, 16 is a good place to start, and I always suggest that people do their own experimentation with their own app, because it really matters what the profile of that app looks like.
Are there any more questions?
I'd like to know if you're using Apache or Nginx in front of Puma, or how that plays out. I mean, compared to a passenger setup.
Sure. So a lot of people do run Nginx, typically Nginx in front of Puma, mostly because Nginx is always going to be faster at serving static assets than Puma will be, mostly because it's just an event loop. It's going to be better and it's got all the Unixy tricks in order to keep that fast. That being said, Puma actually does support slow connections fine. That's always actually that was a big reason that people initially put Nginx or Apache in front of, say, Unicorn, because Unicorn can't deal with slow connections very well. What it does is it actually it locks up the individual processes, and that's sort of an attack. That's called slower rus. that basically causes the web server, you make 16 requests to the web server and you basically never send any data, and now you've actually brought down an entire machine because of the way that Unicorn is written. So Puma doesn't have that problem. It'll actually it gives an advantage to clients that are good clients. So in other words, they send their request very quickly. It will handle them very quickly. If it sees a client is being very slow for whatever reason, it actually has a separate event loop thread that it actually will punt that connection off to. And the event loop thread will monitor it and see and wait for the data to come in. And when it actually finishes coming in, then it will go back. So that way, Puma is fairly immune to that kind of attack. So you can actually expose Puma directly to the public internet, and it will do fine. That being said, like I said, a lot of people do still put Nginx or Apache in front of it because they've got the static assets. That's always the big reason. That's always the big reason.
Cool. I think we're going to say thank you.
Sure.
And we really appreciate you taking the time to speak with us today.
Absolutely.
Yeah.